Hi, my name is Austin Hounsel, and I'm a PhD student in the Computer Science Department at Princeton University. And today I'm going to be talking about some work we've done on exploring the use of infrastructure features to detect disinformation websites. This work was done in collaboration with Jordan Holland, Ben Kaiser, Kevin Borgolte, and Jonathan Meyer from Princeton University, and Nick Feamster from the University of Chicago. So, automated detection is needed to fight disinformation at scale. The problem is that fact checkers can't keep up with disinformation websites on their own. There's simply too many posts being made to social media to manually label each post. However, automated methods in previous work that focus on article content are difficult to scale, since new unverified claims are constantly being released about current events. Similarly, features that focus on the style that an article is written in may not generalize beyond a single dataset. Lastly, our automated methods that focus on social graph features are reactive in nature and not proactive. Ideally, we would like to be able to stop disinformation before it spreads in social media. So if we rely on features related to how a particular post or article is spreading, the damage may already be done. So our key insight in being able to stop disinformation early and at scale is that disinformation websites have similar characteristics to spam and phishing websites. In work on spam and phishing, researchers have been able to successfully engineer network-level features to identify such websites. Our key insight is that disinformation websites also share such network-level characteristics, such as a low cost and quick setup time, a short lifespan, and being hosted on a distinct set of networks. Thus, we distinguish ourselves from prior work on automatically identifying disinformation websites by focusing on what we call infrastructure features, which relate to how a website is constructed rather than its content or how it's shared on social media. So this is a quick overview of all of our infrastructure features that we engineered. I'm not going to go into each feature right now, but this table is available in the full paper. I do want to point out that generally we divide our features into three categories: domain features, certificate features, and hosting features. I'm now going to explain what each of these categories of features mean. So first, we define domain features as features that are available to domain registrars at the time of domain name registration. These features can be extracted from domain names themselves and WHOIS records, which provide information about the registrants of these names. Several key features include the presence of newsy keywords in the domain name, such as Gazette or Herald, the choice of a registrar, and how long ago the domain name was registered. For example, many disinformation websites we find use low-cost registrars to quickly set up a domain name. Similarly, they have shorter lifespans and are more recently registered than traditional news outlets. We also define certificate features as features that are available to certificate authorities at the time of certificate issuance. These features can be extracted from TLS certificates themselves. Several key features include the number of domain names in the subject alternate name field and whether the certificate has actually expired. We lastly define hosting features as features that are available to hosting providers at the time that a website is first deployed. These features can be extracted from the HTML of web pages or the IP address of the server that hosts the web page itself. Several of the key features include the presence of certain WordPress plugins and the autonomous system number that a website is hosted on. For example, we find that disinformation websites typically use low-cost hosting providers, whereas traditional news outlets were more likely to use enterprise-grade hosting providers, such as Encapsula. So in order to evaluate our infrastructure features and their effectiveness in detecting disinformation websites, we created a training dataset of 551 disinformation websites, 553 news websites, and 555 non-news websites. We find that disinformation websites were sourced from fact checkers, academics, and news outlets, which we list these sources in the full paper. We originally had a data set of about 768 disinformation websites, but we found that many of them were actually inactive and no longer serving content. Fortunately, we were able to reconstruct the features from many of these inactive websites, which is how we resulted in 551 disinformation websites in total. We were able to get these features using historical data from sources like the Internet Archive. So to perform an initial evaluation of the effectiveness of infrastructure features, we performed 5-fold cross-validation on our training data. The We first trained a random forest model on our infrastructure features because we expected that feature interpretability would be important for human moderators that might want to use our model. Furthermore, it enabled us to rank our features. As you saw on the earlier slide, with the table that listed all of our features, we had a column where we listed the rank of each feature amongst each other and how important they were in making classifications. We go in more in detail about our hyperparameter selection, thus which parameters we selected, how we arrived at the values for those hyperparameters in the full paper. So the figure on the left shows the mean receiver operating characteristic curve when we perform five-fold cross-validation with our classifier. And the right figure shows precision recall curves for cross-validation. In terms of cross-validation, we find that disinformation websites are actually detectable using infrastructure features. We do see on the figure on the left that the disinformation class performed worse in detection than the news class or the other, or rather non-news class, as we refer to it. But we still did pretty well in terms of our training data and being able to identify disinformation websites. We also see a similar pattern in the precision recall curve. We also find that domain features do pretty well on their own. This is promising because domain features are available very early in a website's life cycle, and they're fairly easy to obtain for a given website. You can just look at a domain name or look up a WHOIS record to obtain the information you need to extract domain features. We do see that certificate features performed pretty poorly on their own, and hosting features seem to do fairly okay. But of course, domain features clearly did the best. So we decided to test our model on real-time data to evaluate how it would perform in the real world when there are new websites being evaluated that we haven't seen before. So we built a system that makes classifications on a live Twitter feed. We used the Twitter streaming API and sampled tweets using the news keyword. Our system ran over 5 days across 2 servers. The first server ingested live data and extracted features, and the second server made classifications in real time. After 5 days, we randomly sampled 100 predictions made for each class and manually labeled the correct classes. So this figure shows a confusion matrix for our real-time performance on a random sample of the Twitter predictions we made. We consciously note that our model's performance radically degraded in performance compared to cross-validation. As you can see, out of the 100 predictions made for disinformation websites, only about 5 actually were true predictions. We were able to do significantly better on news websites and non-news websites, although performance could definitely be improved. So what does this all mean? Why would the performance have so radically degraded? Well, we have a couple of theories. One is that there might be a massive class imbalance in the real-time data between the disinformation class, news websites, and other websites. So as I described earlier in our training data, we nearly equally balance the 3 classes, but in the real world, it might be the case that there are far more news websites and non-news websites being posted to Twitter than disinformation websites. Secondly, some of the data sets we used for our disinformation class were several years old, which were compiled, again, by fact checkers and news organizations. If the infrastructure features for new disinformation websites look significantly different than disinformation websites from several years ago, then our classifier might do okay in cross-validation, but not on real-time data where the features have evolved over time. Third, it may be the case that there are artifacts in how our training data was curated, which negatively impacts the performance on real-time data. For example, about 34% of the disinformation websites on our training data are active, whereas all the news websites are active. So there's a huge difference in terms of how many times we had to reconstruct features for disinformation websites that are no longer active and news websites. So in conclusion, we find that disinformation websites seem to have distinct infrastructure features compared to news websites and non-news websites, which may aid in the detection. Our model did pretty well in cross-validation, but radically degraded in performance in real time. Nonetheless, we argue that infrastructure features have the potential to improve the automatic detection of disinformation. Future work should explore how real-time data differentiates between common data used in research. And it should also explore the scale to which disinformation is posted on social media so that we can more accurately determine what our balance in the training data should be between how many disinformation websites we include and how many news websites we include or non-news websites. So I want to thank you for listening to this talk. We thank our paper shepherd, Jed Crandall, and our anonymous reviewers for their feedback. We note that this work was funded in part by a National Science Foundation award. And any questions or comments, you can reach me at ahounsel@cs.princeton.edu, and I would be happy to talk further.